I never go into a pool without first checking if the pH is well buffered. Because you can't trust my nephew not to pee, and you never know when an aerobics class is going to show up, start huffing and puffing out all that CO2, making the water more acidic. Without a buffer, your pool's pH will be on a wild ride. This is Real Chem. But how does a buffer actually work? How does it absorb the extra acid or base being thrown into our pool? To understand this, we're going to compare, side by side, what happens when we add a small amount of acid or base to pure water versus a buffer solution. At the particulate level, the difference is striking. In pure water, the added hydronium or hydroxide ions just sit there, causing a big shift in pH. But in a buffer, those same ions react with the buffer components, preventing dramatic changes in pH. This side-by-side look will help us see how buffers do their job. Let's start by looking at pure water. What happens when we add a small amount of acid or base? Adding acid introduces hydronium ions, causing the pH to drop dramatically. Adding base introduces hydroxide ions, leading to a significant rise in pH. Even small amounts of acid or base make a big impact. There's nothing in pure water to counteract these changes. Now let's see how a buffer responds differently. A buffer is a mixture of a weak acid and its conjugate base. In this region of our buffer solution, we start with 6 weak acid molecules and 6 conjugate base molecules. First, let's add acid. 2 hydronium ions enter the solution. But unlike in pure water, they don't just stay there. Instead, the conjugate base molecules react with them, neutralizing the added acid. This reaction converts 2 conjugate base molecules into weak acid molecules, leaving us with 8 weak acid molecules and 4 conjugate base molecules. Now, let's add base instead. 2 hydroxide ions enter the solution. This time, the weak acid molecules react with them, neutralizing the base. This reaction converts 2 weak acid molecules into conjugate base molecules, leaving us with 4 weak acid molecules and 8 conjugate base molecules. So what just happened? In both cases, the added hydronium or hydroxide ions didn't just stay in solution, they reacted with the buffer components. Instead of causing a dramatic shift in pH, they were absorbed by the buffer system. But how does that relate to pH? A key idea in buffer chemistry is that as long as both a weak acid and its conjugate base are present in high concentrations, the pH of the solution stays close to the pKa of that acid. The Henderson-Hasselbalch equation helps us relate pH to the ratio of the conjugate acid and base in our buffer. To keep things concrete, we'll consider a weak acid with a Ka of 10 to the minus 8, which corresponds to a pKa of 8. Our starting buffer had equal concentrations of the weak acid and its conjugate base. Since the log of 1 is 0, that means our initial pH equals the pKa of 8. When we added acid, the reaction converted some conjugate base into weak acid. The concentration of the weak acid became twice that of the base. This brings the pH down by 0.30, bringing it to 7.70. When we added base, the opposite happened. The weak acid was converting into conjugate base, making the base concentration twice that of the acid. This raises the pH by 0.30, bringing it to 8.30. So, despite adding acid and base, the pH remains stable, staying within 0.30 of our initial buffer pH of 8. That's the power of a well-designed buffer. So, in buffering our pool, we ensure it has large concentrations of both the weak acid and its conjugate base, ready to handle whatever gets thrown in, literally. Any acid or base that gets into the water reacts with the buffer instead of just building up in solution, whether from swimmers, splashes, or my 3-year-old nephew. This shifts the balance between the weak acid and conjugate-base components of our buffer system, nudging the pH slightly, but keeping it under control. Thanks to the buffer, our pool's pH stays stable.